So today we're going to be evaluating a function. Now this is going to be a new form of what an equation looks like. This is function notation to be exact. And what this shows is that we have this machine called f. And it takes some sort of input or some sort of fuel to make it run. And once we plug it in there and the machine starts whirling, it gives us something. So the equivalent of if we plug gasoline input into the machine called f, it will give us motion. It will translate that gasoline into something that puts the car forward, and we have an output. And that output is that we get to move from point A to point B much faster than by walking. By comparison, that if I input meat into a grinder, the output would be sausages or hamburger patties. So the F is the thing, either the car or the grinder or whatever machine we have. The input is what we need to plug in, and the output is what we get. So let's take a look at this machine. This machine, or this function called f, requires that we plug in an x value. And it's going to output, it's going to square that x value for us. So when I see this, that says, hey, go get the machine, plug in 2, wherever I see an x. So I'm going to go ahead and I'm going to write this equation with an x ready to go. And I'm going to take that and I'm going to plug the 2 right where I would normally see that x. Now, here's the thing. We know that this is 2 squared. So the idea is that if we remember our rules, the square means that I'm going to multiply this number times itself twice. So I'm going to have 2 of these 2's. So 2 and 2. Actually, I'm even going to write that off to the side. So a square means we write the number twice, or number, yeah, I guess in this case, number twice. So if I have something like a 3 cubed, how many times would I write that 3? 1, 2, 3. If I had 3 to the 4th, I would write that 3 1, 2, 3, 4 times. So that's kind of what's going on right here. So back to our example here. I know that I've plugged in the number 2 and I've squared it, boop, boop. Now I just need to multiply 2 by 2, gives me a 4. And then I have my function, when I plugged in a 2, gives me the answer of 4. Now this is an important point because a lot of students feel they're saying, well, if I'm multiplying f by 2, don't I go ahead and divide so that I can solve for f? And if this was an equation, yes, you would be correct. But again, this is not an equation. Today we're going over functions. With a function, we typically never bother with the left side of the equation, or with the left side of the function. This is what we plugged in. This is what we plugged it into. So this is our function called f, and this was our answer. And so typically a function, the final answer is written in this format. You can see what was plugged into the machine, what the machine's name was, and what you got after you plugged it in. So a big thing that students often like to do is they like to do something like this, where they'll take, okay, well, f of 2, doesn't that equal the same thing as 2 times f? And then in that case, I would go ahead and I would divide by 2, and so f equals 2, and they would box that up. This is not what we want to do. Remember, a function notation, we're leaving that. We preserved that from the beginning. We plugged a 2 into this function and got our answer of 4. So now that we've covered a little bit of the basics of that, let's go ahead and let's try another one. Now this function called f has a variable called r, meaning we need to figure out what value of r we plug in, and it's going to take r and it's going to double it, and then it's going to take away 10. So before we even look at our value on our function right here, let's go ahead and get that set up so that whatever I need to plug in, I'm ready to plug in. And then we can look at what value are we plugging in. Well, I'm plugging in an 8. And so remember the order that we said we were going to do this in. We were going to double it because now we're following order operations. So that becomes a 16, and then I take away 10. So 16 take away 10 is 6. And so my final answer is my function, my machine, when I plugged in the number 8, I got an answer of 6. Perfect. And so you might ask, well, what happens if I need to plug in a negative number? Well, negative number works just the same. I say I have some function, some machine called f. I'm plugging in the number y, or some input called y, and I'm going to multiply that number times 4 and take away 21. So let's see if I say 4 multiplied by some number, take away 21. I'm going to plug in this negative 4. And so again, I'm going to follow order operations on what I would have done up top and say, multiply these two numbers, so I get a negative 16, and I take away 21. I have two negatives, so my answer is also going to be negative when I'm adding or subtracting. So negative 16 and negative 21, I'm going to break that into two pieces. Negative 16 and 1 is negative 17. Negative 17 and 20 is going to be negative 37. And so my function, when I plugged in the number negative 4, gave me a negative 37. So what I want you to do is I want you to try number 7. Go ahead, pause the video, give it a shot, unpause it when you're done, and see how well you did. Okay. So by this time you should have said, hey, I'm going to square this number, whatever that number is, and then I'm going to add 9. And we know that the number that we're going to be squaring is a negative 10. Remember from what we talked about earlier, that square power means that I write that negative 10 out twice. So I say, okay, negative 10 times negative 10. I still have the plus 9. That's going to be off to the side. We know a negative times a negative is going to be a positive 100 plus 9. So this is going to be a 109. And one of the reasons why we wanted to show this one is the fact that oftentimes when students want to square a negative number, they'll do a very good job of saying, well, negative 10 squared, and they'll look at that as a negative 10 squared, and they'll square the 10 and say, well, that's 100, and they'll get a negative 100, and when they add the 9, they'll get a negative 91. Now, very good in theory, but remember, with a square power, we're writing the number out twice, so I'm multiplying a negative 10 times another negative 10. I'm not just squaring the 10 and then keeping the negative. So let's go ahead and let's try a few more of these. Let's try a few with something like this. Now this is a function called g, and I'm plugging in the variable y. So I need to have some value for y, but what we notice is the fact that I see y popping up more than once in this function rule. And that's perfectly okay. It just means that wherever we go, I have to not only plug in a y right after the negative 2, but I also have to plug in a y right after the 4. Now, you could actually combine these like terms and just plug it in once, but the idea is that what we're going for here is I'm going to plug it in both times for later similarity, I guess we should say. So I'm going to go ahead and I'm going to plug in the value of 3 anywhere that I see a y. That just means I have to plug it in here, and I have to plug it in later on over here. So if I read the original function, it looks like I'm multiplying y times negative 2, which is going to give me a negative 6, and then multiplying y times 4, so over here that's going to get me a 12. So my function is going to be negative 6 plus 12, which is going to give me a positive 6. Oop, almost wrote a g. It's my g of 3. If you believe that's a g really hard, it will be. So g of 3 is 6. And so same idea no matter what the function looks like. Wherever I see the variable, this function called g needs a variable called w, and I see w pop up in 2 different locations. Now I could try and combine these together, but what I'm going to notice is that this w is on the top and this w is on the bottom, so they're not really going to cancel each other out like the earlier one would. So I'm just going to embrace it and say it's going to be 1 divided by that number plus that number, whatever number we want to plug in. And in this case, I'm plugging in another 3. And so I have 1/3 plus 3. And now this brings us back to another separate point, is that when I'm converting this 3, I have to add 1/3 and 3. So let me go ahead and pull this so that we can set up a nice little aside. I'm going to be adding 1/3 plus the whole number of 3, which I can't add a fraction and a whole number just across. Oftentimes what students will try and do is they'll say, okay, 1 plus 3 is 4, and they'll get 4/3, and that, we know, cannot work. What we have to do instead is we have to take that 1/3 and somehow convert the 3, which currently is in a whole unit. I need to split it up into a third. And so, albeit the visual way is to take those 3 units and literally carve them into 3 slices each and count them, there's an easier way. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I know this is going to end up being 9/3. But again, there's an easier way. I need to convert this 1 into a 3. So I'm going to ask myself, 1 times what number is 3? And you might say, hey, if I multiply that times 3, that'd be good. But wait, isn't that just converting what this number is? And you would be correct. So what we're going to do is we're going to say, how about this? Times 3 divided by 3. Because don't those cancel out if I multiply by 3 and then divide? So what this will do is if I look at this in its own thing, 3 divided by 3 is 1. I'm not actually changing this at all. So I'm going to say, I'm going to leave the 1/3, and I'm going to take top times top and bottom times bottom. Boom, we have our 9 that we know we were going to get earlier, 9/3. But what we did was we allowed to change it simply by saying multiply by that other denominator. Now that they're both in thirds, I can successfully pair up these denominators so that I can just focus on their numerators. So because they're both over 3, I'm going to say they're both thirds. This one had 1, this one had 9, which is going to give me 10/3. And actually, I kind of skipped ahead there. So I had 1/3, and our newly converted 3 is going to be 9/3, which is going to give me my 10/3. So my G evaluated out at 3 is going to give me 10/3. Perfect. And so I've got 2 more. I want you to go ahead and pause the video, resume it when you're done, and see how well you do on these. These are a little bit more challenging, but give it a shot. See how well you do. Okay. So for these last 2, what we should notice is the fact that these are, again, something where I'm going to have to plug in my number more than once. Here, I'm going to have to square the number first, and then I'm going to double it. So what I've got going on right here is I am going to square the number -2. And then I'm going to multiply -2 times 2. And again, we remember that the square power means I write it out more than once. Let's not forget that a lot of students, what they might try and do is they might try to take the -2 and multiply it by 2, which is very tempting, but we know that's not how an exponent works. An exponent takes that number, -2, and we have to write it that many times. So 2 times. And I'm just going to go ahead and leave this 2 times -2 over here, and I'm not going to do anything to it just yet. Okay? And then what we're going to do is I'm going to combine these 2 terms, and I'm going to combine these 2 terms. So I'm going to say -2 times 2, or -2 times -2 is going to give me a +4. +2 times -2 is going to give me a -4. And 4 take away 4 is 0. So G of -2 is equal to 0. Perfect. And the second one, this very, very last one, this was the most challenging because it pulled the same topic from up here just to make sure we know how to do everything. I'm going to take whatever number I have and I'm going to square it, and then I'm going to cut it in half, and I'm going to add the 2 things together. So we have to pull out all the stops with how we've done everything today because this uses all the skills. our first thing we know is that with a power, what we're going to have to do is we're going to have to write that number out twice. So 3 over 2 times 3 over 2 plus 1 over 2 times 3 over 2. We know that when fractions are side by side and I'm multiplying them, I just multiply the top two, so 3 times 3, and the bottom two. So 2 times 2 is 4. Same thing over here, top times top, 3, bottom times bottom, 4. And then we look, and do these both have the same denominator like we did earlier? Yes, they do. So we don't actually need to worry about converting any of the denominators. So 9 plus 3 is going to give us a 12 over 4, which we realize this 12 over 4 can actually reduce one more time into a 3 over 1 or just 3. So we know the answer to our equation, or the answer to our function is, nope, not f. G evaluated out at 3/2 is equal to 3. Boom, and there we go. So today we're going to be doing more evaluating of functions, but we're going to be doing within an added aspect. We're going to be doing function evaluation of a piecewise function. Now, the whole idea is that we're going to be evaluating the appropriate piece considering the domain restrictions listed after each piece. This function, called f, which needs an x plugged in, has two different parts. It's either cutting the number in half, or it's changing the sign on the number, depending on if the number is less than -2 or greater than -2. So we're going to have to consider what number we plug in. It may or may not be the same one each time. So let's take a look at our first question. I have the function called f, and I'm evaluating the number 5. So normally, what we would do is we would take this part of the function, and we would rewrite it and say, let's plug in 5. But we would get two answers. So let's take a pause, and let's look and say, am I plugging into the 1/2 or the -x? Well, it depends on where -5 is. If I have a number that's less than -2, or if a number is greater than or equal to -2. 5 is going to fall into the latter, so I'm actually plugging it into the part of the function which is -x. So I'm going to evaluate this function out and say it's a negative, whatever we plugged in. In this case, it's going to be 5. So this was just a one-step function. F of 5 is -5. And the same for the f of -5. I'm going to see which part of the function I'm going to use depending on what that value is. -5 is going to be less than -2. So I'm plugging it into the top part of the function. I'm going to say it's 1/2 of whatever that number is. So I'm going to get this set up so I can plug in whatever number I need. In this case, we're plugging in the -5. And we know that we can't just willy-nilly multiply a fraction times a whole number. What we have to set up is 1/2 times -5 over 1. This allows us to check for any cross reduction that we could be doing. And if not, we just multiply top times top, which is -5, and then bottom times bottom, which is 2. So perfect. F of -5 is -5/2. Perfect. So let's try one a little more complex. This one deals with absolute values. I have a function called y, so some machine, or not a function called y. I have some machine called f that needs y's in order to work. Well, if those y's are small and less than 2, I take the absolute value and multiply it by 7. If those y's are large, greater than or equal to 2, I take the absolute value and multiply by 2. So with my first question where I'm plugging in a -1, -1 is going to fall into that first category of a number less than 2, so I'm going to plug it into this part of the function. So 7 times the absolute value of whatever we want to plug in. In this case, I'm plugging in a -1. And we know that the absolute value makes whatever number that is inside there positive. This is going to end up being the it's going to end up being 7 times the absolute value of -1, which is a positive 1. And it's not saying 7 plus 1. That is now a positive 1. 7 times 1 is 7. So f of negative 1 is equal to 7. And so for our second piece, this function, I'm going to plug in a 10. And I'm going to say, well, it doesn't fall into the first category, but it's definitely larger than or equal to 2. So I'm going to plug it into 2 absolute value of y. So 2 times the absolute value of whatever we want to plug in there. In this case, we're plugging in the larger number, 10. And oftentimes what students want to do at this point is they say, well, if absolute value makes a negative number positive, wouldn't it make a positive number negative? Now, albeit that's good logical thinking, it's not the case here. Anytime we see an absolute value bracket, we know that before we've used those brackets and we see those lines, we have to check inside. Can I simplify this? Nope. Well, let me make it positive. And our 10 already is. So we're going to leave it as a positive 10. I think that actually looks a little nicer than what we did over there. So we're going to be writing like that from now on. So 2 times positive 10 is going to give me a positive 20. Perfect. And so this last little piece, we have a function called f where we're plugging in a w. Why don't you go ahead, pause the video real quick, and give this one a shot, and unpause it when you're done. Okay. So for your first one, I'm plugging in the value of negative 1. Now, because it looks like my boundary is at negative 1, it's neither greater than nor less than itself. We have to go a little further and say, hey, the top one is for values that could possibly also equal negative 1. So I'm going to plug in that into this top portion of the function. So 5w squared. So it's going to be 5 times whatever the number is squared. And in this case, I'm plugging in a negative 1. And we remember from previous videos the fact that anytime I have a square power, what I'm doing is I'm writing out that number twice. I'm not multiplying negative 1 times 2. I'm saying this is 5 times negative 1 times negative 1. I'm writing out that number that's at its base 2 separate times. So I'm going to say 5 times negative 1, the first one, is going to be negative 5. And then negative 5 times negative 1, the second one, is going to turn that back into a positive 5. Perfect. So now my function evaluated at negative 1 is going to be equal to a positive 5. For the second part, f of negative 2 is also less than or equal to negative 1. So we're going to use that same part of the function again, 5w squared. We actually didn't even need to use the second one, so we could theoretically scratch it out because neither of our inputs required that part of the function to be used. So I'm going to say 5 times whatever that number is squared. And in this case, I'm plugging in a negative 2. And again, we remember the fact that a square power means that we write out the number a square amount of times, or 2 times. So 5 times negative 2 times negative 2. 5 times the first negative 2 is going to be negative 10. 10 times the second, or negative 10 times the second negative 2 is going to be positive 20. So my function evaluated at negative 2 is going to be a positive 20. Perfect. So I hope you got a good idea from there. Let's give a slightly larger option here. I have not 1, not 2, but 3 different parts on this function. So oftentimes when students see this, they freak out. 3 is no harder than 2, no harder than 4. I could give you 12 different parts. The only thing that you're checking for is you're checking to see where does 9 fit into this function. Does it plug into the first part, the second part, or the third part? Kind of like a coffee machine. This says, hey, if you're trying to plug in the coffee, plug it in the top. If you have water, plug it into the reservoir. And if you have a cup, stick it underneath. If you tried to stick the cup in the top part of the coffee machine, it wouldn't work. Likewise, if you put the coffee in the reservoir, you'd probably break your machine. We just got to figure out where does the part that we have fit into this piecewise function. In this case, 9 is not less than -3, is not between -3 and 4, but in this case, it's greater than or equal to 4. So it's going to be the square root of 4 times that number. So we're going to say the square root of 4 times whatever number we want to plug in. In this case, it is a 9. So the square root of 4 times 9 is 36. And this is asking us what number multiplied by itself gives me 36. And if you said 6, yes, you're correct. The second part's going to be a little easier. I'm going to say, okay, I have this number 0. I want to figure out, do I plug it into the top of the coffee machine in the reservoir, or do I stick my cup beneath where the coffee pours out? In the case of 0, it looks like I'm sticking it in the reservoir, in between -3 and 4, which is going to be the square root of 3x. So I'm going to say it's the square root of 3 times that number. And the number we're plugging in is 0. So with the square root, with the radical, I'm going to say 3 times 0 is 0. And like 36, I'm going to say what number multiplied by itself gives me 0? 0. So my function evaluated at 0 is 0. Perfect. So why don't you go ahead and take a shot at one of the next ones. On 17 and 18, these both fit for this function, and for 21 and 22, this fit for this function. So go ahead, pause the video, give these two a shot, unpause it when you're done, and see how well you did. Okay. So for -1, I'm going to look and say, okay, I see that my -1 is at the barrier, but it can't fit here because I don't have an inclusion aspect in my inequality, only on the bottom when y is greater than or equal to 1. So I'm going to take that 3 and divide it by the number, which means 3 divided by whatever number we want to plug in this case a 1, and luckily 3 does divide by 1, we get 3. So my f of 1 is 3. Likewise, my -5 also almost fits in this middle part, but it doesn't quite fit in there. This is, I guess you would consider the equivalent of like a watery coffee. You're not really sure whether or not it fits into the coffee part or the water part. Probably a bad example, so let's just go ahead and do this. The -5 is the included part on this top here, so it's going to be 1 divided by y, the top aspect of the function. So it's 1 divided by that number. The number that I am dividing by is a -5. 1 doesn't divide by -5, so I'm going to go ahead and leave that as a -1/5. And now what many of you might say is, well, isn't the 5 the negative part? And remember, with a 1/5 like that, you can have the negative in any part. If you wanted it a -1/5, that's the same thing as saying 1 over -5, which is the same thing as saying -1/5. As long as they only have one negative sign, if it's in the top, the bottom, or in the middle, they're all the same thing. And for the last one, our f of -3, we know we're going to plug it in where the w is into this function. We don't fit it in the top nor in the bottom, but it's right here at the middle, right on the edge. So I'm going to say the absolute value of w minus 1. So I'm going to take the absolute value of that number and then take away 1. Luckily, the absolute value of -3 is +3, and I'm going to take away 1. So 3 take away 1 is 2. Perfect. Likewise, f of 1, if -3 was on this end of the barrier, 1 is on the other end of the barrier, but it's still right on the other edge of my absolute value of w, take away 1. So I'm going to take the absolute value of whatever number I plug in and then take away an additional unit. And just like we said before, the absolute value brackets, when we use their power, whatever number is inside becomes a positive version of that number. In this case, it wasn't positive, we made it positive. Here it's already positive, so not a whole lot of work is having to go into this to keep it a positive number. 1 take away 1 is going to give me 0. The function f evaluated when we plugged in the number 1 gave me the answer of 0. And there we go.